Introducing closures. Closures are self-contained blocks of code that can be passed around and used throughout your application code. We can think of an int type as a type that stores an integer and a string type as a type that stores a string. In that context, the closure can be thought of as a type that holds a block of code. What this means is that we can assign closures to a variable, pass them as arguments to functions, and also return functions from them. Closures have the ability to capture and store references to any variable or constant from the context in which they were defined. This is known as closing over the variables or constants, and the best thing is, for the most part, Swift will handle the memory management for us. The only exception is when we create a strong reference cycle, and we will look at how to resolve this in the strong reference cycles with closures section of this chapter. Closures in Swift are similar to blocks in Objective-C. However, closures in Swift are a lot easier to use and understand. Let's look at the syntax used to define the closure in Swift. As we can see, the syntax used to create the closure looks very similar to the syntax we use to create functions in Swift, and actually in Swift the global and nested functions are closures. The biggest difference in the format between closures and functions is the in keyword. The in keyword is used in place of curly brackets to separate the definition of the closures, parameter and return types from the body of the closure. There are many uses for closures, and we will go over a number of them later in this chapter, but first we need to understand the basics of closures. Let's start by looking at some very basic uses for closures so that we can get a better understanding of what they are, how to define them, and how to use them. Simple closures. We will begin by creating a very simple closure that does not accept any arguments and does not return any value. All it does is print hello world to the console. Let's take a look at the following code. Let clause 1 is curly braces function returns void in println hello world and curly braces. In this example, we create a closure and assign it to the constant clause 1. Since there are no parameters defined between the parentheses, this closure will not accept any parameters. Since the return type is defined as void, this closure will also not return any value. The body of the closure contains one line that simply prints hello world to the console. There are many ways to use the closures. In this example, all we want to do is call it. We can execute this closure like this clause 1 function. When we execute the closure, we will see hello world printed to the console. At this point, closures may not seem that useful, but as we get further along in this chapter, we will see how useful and powerful the closures can be. Let's look at another simple closure example. This closure will accept one string parameter named, but will still not return a value within the body of the closure. We will print out a greeting to the name passed into the closure through the name parameter. Here's the code for this second closure. Let clause 2, etc. This is the code. The big difference between clause 2 defined in this example and the previous clause 1, the closure, is that we define a single string parameter between the parentheses in this closure. As we can see, we define parameters for closures just like we define parameters for functions. We can execute this closure the same way that we execute clause 1. The following code shows how to execute the clause 2 closure. This example, when executed, will print the message hello John to the console. Let's look at another way we can use the clause 2 closure. Our original definition of closure states closures are self-contained blocks of code that can be passed around and used throughout the application code. What this tells us is that we can pass our closure from the context that they were created in, other parts of our code. Let's look at how to pass our clause 2 closure into a function. We will define the function that accepts our clause 2 closure like this. We define the function just like we would any other function. However, in our parameter list, we define a parameter named handler, and the type defined for the handler parameter is string, returns nothing. We define the function that accepts our clause 2 closure like this. We define the function just like we would any other function. However, in our parameter list, we define a parameter named handler, and the type defined for the handler parameter is string, returns nothing. Void. If we look closely, we can see that the string returns void. The definition of the handler parameter matches the parameter and the return types that we defined for close to closure. This means that we can pass the close to closure into the function. Let's look at how to do this. Test closure close to. We call the test closure function, just like any other function, and the closure that is being passed in looks like any other variable. Since the close to closure executes in the test closure function, we will see the message hello dash printed to the console when this code is executed. As we will see a little later in this chapter, the ability to pass closures to functions is what makes closures so exciting and powerful. As the final piece to the closure puzzle, let's look at how to return a value from a closure. The following example shows how to return a value from a closure. The definition of the close to closure looks very similar to how we defined close to closure. The difference is that we changed the void return type to a string type. Then in the body of the closure, instead of printing the message to the console, we used the return statement to return the message. We can now execute the close 3 closure just like the previous two closures, or pass the closure to a function like we did with the close 2 closure. The following example shows how to execute the close 3 closure. After this line of code is executed, the message variable will contain the hello body string. The previous 3 examples of closures demonstrate the format and how to define a typical closure. For those who are familiar with Objective-C, we can see that the format of closures in Swift is a lot cleaner and easy to use. The syntax for creating closures that we have shown so far in this chapter is pretty short. However, we can shorten it even more. In this next section, we will look at how to do this. Shorthand syntax for closures. In this section, we will look at a couple of ways to can shorten the definition of closures. To use the shorthand syntax for closures is really a matter of personal preference. There are a lot of developers that like to make their code as small and compact as possible, and they take great pride in doing so. However, at times this can make code hard to read and understand by other developers. The first shorthand syntax for closures that we are going to look at is one of the most popular, and is the syntax we saw when we were using algorithms with arrays in chapter 3, using collections and Cocoa data types. This format is mainly used when we want to send a really small, usually one line, closure to a function like we did with algorithms for an array. Before we look at this shorthand syntax, we need to write a function that will accept the closure as a parameter. This function accepts 2 parameters. The first parameter is an integer named num, and the second parameter is a closure named handler that does not have any parameters and does not return any value. Within the function, we create a for loop, then that will use the num integer to define how many times it loops within the for loop. We call the handler closure that was passed into the function. We can create the closure and pass it to the test function in this way. This code is very easy to read and understand, however it does take 5 lines of code. Now let's look at how to shorten this code by writing the closure in line within the function call. In this example, we created the closure in line within the function call using the same syntax that we used with algorithms for arrays. The closure is placed in between two curly brackets, which means the code to create our closures is the println hello world from shorthand closure. When this code is executed, it will print out the message hello from shorthand closure 5 times on the screen. 5 times on the screen. In chapter 3, using collections and Cocoa data types, we saw that we were able to pass parameters to the array algorithms using the $0, the $1, $2, and so on parameters. Let's look at how to use parameters with the shorthand syntax. We will begin by creating a new function that will accept the closure with a single parameter. We will name this function test function 2. The following example shows what to new test function to the function. In test function 2, we define a closure like this: name plus colon string returns void. This definition means that the closure accepts one parameter and does not return any value. Now, let's see how to use the same shorthand syntax to call this function. The difference between this closure definition and the previous one is $0. The $0 parameter is shorthand for the first parameter passed into the function. If we execute this code, it will print out the message hello from me 5 times. Using the $sign followed by a number with inline closures allows us to define the closure without having to put a parameter list in the definition. The number after the $sign defines the position of the parameter in the parameter list. Let's examine this format a bit more because we are not limited to only using the $sign and number shorthand format with inline closures. This shorthand syntax can also be used to shorten the closure definition by allowing us to leave the parameter names of the following example demonstrates this. In this example, our closure has 2 string parameters defined. However, we do not give them names. The parameters are defined like this: string. We can then access the parameters within the body of the closure using $0, $1. Also, note that the closure definition is after the colon, using the same syntax that we used to define the variable type, rather than inside the curly brackets. When we use anonymous arguments, this is how we would define the closure. It will not be valid to define the closure like this. In this example, we will receive the error: anonymous closure arguments cannot be used inside the closure that has explicit arguments. We will use the close 5 closure like this: close 5 hello Kara. Since hello is the first string in the parameter list, it is accessed with $0. And as Kara is the second string in the parameter list, it is accessed with $1. When we execute this code, we will see the message hello Kara printed to the console. This next example is used when the closure doesn't return any value. Rather than defining the return type as void, we can use parentheses like the following example shows. In this example, we define the closure like this: function returns function. This tells Swift that the closure does not accept any parameters and also does not return a value. We will execute this closure as follows: close 6 function. We have one more shorthand closure example to demonstrate before we begin showing some useful examples of closures. In this last example, we will demonstrate how we can return a value from the closure without the need to include the word return. If the entire closure body consists of only a single statement, then we can omit the return keyword and the results of the statement will be returned. Let's take a look at an example of this. In this example, the closure accepts 2 parameters of the int type and will return an int type. The only statement within the body has 2 parameters together, but if you notice, we do not include the return keyword before the additional statement. Swift will see that this is a single statement closure and will automatically return results, just as if we put the return keyword before the addition statement. We do need to make sure that the result type of our statement matches the return type of the closure. All of our examples that were shown in the previous 2 sections were designed to show how to define and use closures on their own. These examples did not really show off the power of closures, and they did not show how incredibly useful closures can be. The remainder of this chapter is written to demonstrate the power and usefulness of closures in Swift. Using closures with Swift's array algorithms. In Chapter 3, using collections and Cocoa data types, we looked at several built-in algorithms that we could use with Swift arrays. In that chapter, we briefly showed how to add simple rules to each of these algorithms with very basic closures. Now that we have a better understanding of closures, let's see how we can expand on these algorithms using more advanced closures. In this section, we will primarily be using the map algorithm for consistency purposes. However, we can use the basic ideas demonstrated with any of the algorithms. We will start by defining an array to use var guests John, Kim, Kaylee, Kara. This array contains a list of names and the array is named guests. This array will be used for all examples in this section except for the very last ones. Now that we have our guests array, let's add a closure that will print a greeting to each of the names in the guest array. Since the map algorithm applies to the closure to each item of the array, this example will print out a greeting for each name within the guest array. After the first section in this chapter, we should have a pretty good understanding of how this closure works using the shorthand syntax that we showed in the last section. We could reduce the preceding example down to the following single line of code. This is one of the few times, in my opinion, where the shorthand syntax may be easy to read than the standard syntax. Now, let's say that rather than printing the greeting to the console, we want to return a new array that contains the greetings. For this, we will return a string type from our closure, as shown in the following example. When this call is executed, the message array will contain a greeting to each of the names in the guest array, while the guest array will remain unchanged. The preceding examples in this section will show how to add the closure to the map algorithm in line. This is good if we only had one closure that we wanted to use with the map algorithm. But what if we had more? But what if we had more than one closure that we wanted to use? If we wanted to use the closure multiple times or reuse them with different arrays. For this, we could assign the closure to a constant or variable and then pass in the closure using its constant or variable name. As needed, let's see how to do this. We will begin by defining two closures. One of the closures will print a greeting for each name in the guest array. And the other closure will print a goodbye message for each name in the guest array. Now that we have two of our closures, we can use them with the map algorithms as needed. The following code shows how to use these closures interchangeably with the guest array as follows. Whenever we use the greet guest closure with the guest array, the greetings message is printed to the console. And whenever we use the say goodbye closure with the guest array, the goodbye message is printed to the console. If we had another array named guest2, we could use the same closures for that array, as shown in the following example. All of the examples in this section so far have either printed a message to the console or returned a new array from the closure. We are not limited to such basic functionality in our closures. For example, we can filter the array within our closure, as shown in the following example. In this example, we print out the different messages depending on whether the name starts with the letter K or not. As we mentioned earlier in the chapter, closures have the ability to capture and store references to any variable or constant from the context in which they were defined. Let's look at an example of this. Let's say that we have a function that contains the highest temperature for the last 7 days at the given location, and this function accepts the closure as a parameter. But I have coffee here around here, man. I haven't drank my coffee in 60 years. Bismillah. Now that's coffee drinking. We're gonna quit this Swift thing. Leave it to tomorrow. What we're going to do now? Now we're going to start with, we had JavaScript a little bit yesterday, and these are the folders I've downloaded. We cannot check them out because I'm not connected with my Bluetooth. So what we're going to do is check out what we have open here. Check out what we have open. This is the way it goes. And this is what we want to stay. And that's the way we're going to go. And that's the way we're going to wait. This so it rhymes. It rhymes. You know what that rhyme? You know what rhyme is? Rhyme is the malicious things that hooked and parallel across them. Restate the sum of voltage drop from the A to the B via one path to a circuit equals sum by any other root, and is named important capital. That's what I call the hint. It's a big hint. To say something like the voltage to the resistor is nonsense. However, we do frequently speak of the voltage at the point that we're still recording. Voltage at the point in the circuit. This is always understood to mean the voltage between that point and the ground, a common point in the circuit that everyone seems to know about. Soon you will too. We generate voltages by doing work on charges in devices such as batteries, conversion of electrochemical energy generators, conversion of mechanical energy by magnetic forces, solar cells, photovoltaic, conversion of the energy of photons, etc. We get currents by placing voltages across things. At this point, you may well wonder how to see voltages and currents. The single most useful electronic instrument is the oscilloscope, which allows you to look at the voltages, or occasionally currents, in a circuit and as a function of time. We will deal with oscilloscopes and also voltage meters when we discuss signals shortly for preview. See Appendix 0 and the multimeter box later in this chapter. In real circuits, we connect things together with wires and metallic conductors, each of which has the same voltage on it everywhere with respect to ground, say. We mention this now so that you will realize that an actual circuit doesn't have to look at like its schematic diagram, because wires can be rearranged. Here are some simple rules about the voltages and currents. The sum of the current into a point and into a circuit equals the sum of the currents out of the conversion of the charge. This is something like the Kirchhoff's law, CL. Engineers like to refer to such a point like a node. It follows, for a series circuit with a bunch of two terminals, things all connected end to end. The current is the same everywhere. Things hooked in a parallel figure 1.1 have the same voltage across them. Restated, the sum of the voltages drops from A to B via one path to a circuit equals to sum by any other root. And it's simply the voltage between A and B. Another way to say they say that the sum is the voltage that drops around and the closed circuit is zero. This is Kirchhoff's voltage law, KVL. The power energy unit per minute consumed by a circuit device is, this is simply energy charge time, for V and volts and I in amps. P comes out in watts. A watt is a joule per second. 1 W is 1 J per second. So for example, the current flowing through a 60 watts light bulb running on 120 volts is 0.5 amperes. Power goes into heat, usually or sometimes mechanical work, motors, radiators, energy lamp, transmitters, or stored energy, batteries, capacitors, inductors. Managing the heat load in a complicated system, meaning a large computer, in which many kilowatts of electrical energy are converted to heat, with the energetically insignificant byproduct of a few pages of computational results, can be a crucial part of the system design. Soon, when we deal with periodically varying voltages and currents, we will have to generalize. The simple equation P is V1, or VI meant, to deal with average power, but is correct as the statement of instantaneous power just as it stands. Incidentally, don't call current amperage, that's strictly Bush League. The same caution will apply to the term ohmage when we get to resistance in the next section. 1.2.2 Relationship between voltage and current resistors. This is a long and interesting story. It is the heart of electronics. Crudely speaking, the name of the game is to make and use gadgets that have interesting and useful I versus V characteristics. Resistors I is simply proportional to V. Capacitors I proportional to rate of change of V. Diodes I flows in only one direction. Thermistors temperature depending resistors. Photoresistors light depending resistors. Strain gauge strain dependent resistor, etc. are examples. Perhaps more interesting still are three terminal devices, such as transistors, in which the current that can flow between the pair of terminals is controlled by the voltage applied to the third terminal. We will gradually get into some of these exotic devices. For now, we will start with the most fun, mundane, and most widely used circuit elemental resistor, figure 1.3. MashaAllah tabarakallah. MashaAllah tabarakallah. A. MashaAllah tabarakallah. A. Resistance and resistors. Resistance and resistors. It is an interesting fact that the current through a metal is conductor or other partially conducting material is proportional to the voltage across it. In the case of wire, prefixes, multiple prefix symbol and derivation. 10 to the power 24, jota, ye, and 1 of Latin alphabet, hint of Greek iota. 10 to the power 21, zeta, z, and of Latin alphabet, hint of Greek zeta. 10 to the power 18, exa, e, Greek hexa, 6 power of 1000. 10 to the power 15, peta, p, Greek penta, 5 power of 1000. 10 to the power 12, tera, t, Greek teras, monster. 10 to the power 9, giga, g, gigas, giant. 10 to the power 6, mega, megas, great. 10 to the power 10, kilo, k, Greek, kihiloi, 1000. 10 to the power minus 3, milli, m, Latin, milli, 1000. 10 to the power minus 6, macro, mikros, small. 10 to the power 9, nano, n, Greek nanos, dwarf. 10 to the power minus 12, pico, p, from Italian, Spanish, piccolo, pico, small. 10 to the power minus 15, femto, f, Danish, Norwegian, femten, 15. 10 to the power minus 18, eto, a, Danish, Norwegian, 18. 10 to the power minus 21, zeto, z, end of the Latin alphabet, mirrors, zeta. 10 to the power minus 24, yocto, y, and 1 of Latin alphabet, mirrors, jota. These prefixes are universally used to scale units in science and engineering. Their etymological derivations are a matter of some controversy and should not be considered historically reliable. When abbreviating a unit with a prefix, the symbol for the unit follows the prefix without space. Be careful about application of lowercase letters, especially m and m, in both prefix and unit. In m, in 1 megawatt is a milliwatt, or 1,000 of a watt. 1 megahertz is a megahertz, or 1 million hertz. In general, units are spelled out with lowercase, with letters, even when they are derived from proper names. The unit name is not capitalized when it is spelled out and used with the prefix, and only when abbreviated, thus hertz and kilohertz. But hertz, But hertz and kilohertz, watt, milliwatt, megawatt, but watt, megawatt, and megawatt. Conductors used in circuits. We usually choose a thick enough gauge of wire so that these voltage drops will be negligible. This is by no means the universal law for all objects. For instance, the current through a neon bulb is a highly non-linear function of the applied voltage. It is zero up to a critical voltage, at which it rises dramatically. The same goes for a variety of interesting special devices, diodes, transistors, light bulbs, etc. If you are interested in understanding why metallic conductors have behaved this way, read chapter 4.4-4.5 and Purcell and Molin's splendid text Electricity and Magnetism. A resistor is made out of some conducting stuff, carbon or thin metal carbon film, a wireproof for poor conductivity, with the wire contacts. At each end is characterized by the resistance. R is in ohms, for V is volts, and I in amps. This is known as Ohm's law. Typical resistors are the most frequently used type metal oxide film. Metal film or carbon film come in values of from 1 ohm to about 10 megaohms, 10 ohms. Resistors are also characterized by how much power they can safely dissipate. The most commonly used ones are rated at 1/4 or 1/8 watt. Their physical size and by other parameters such as tolerance, accuracy, temperature with coefficient أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Temperature coefficient, noise voltage coefficient. The extent to which R depends on applied V stability with time inductance is utilized to the box on resistors. Chapter 1X and Appendix C for further details. Figure 1.2 shows us a collection of resistors with most of the available morphologies represented. Roughly speaking, resistors are used to convert a box. We bumped into a box. Resistors are truly ubiquitous. There are almost as many types as there are applications. Resistors are used in amplifiers as loads for active devices, in bias networks, and as feedback elements. In combination with capacitors, they establish time constants and act as filters. They are used to set operating currents and signal levels. Resistors are used in power circuits to reduce voltage by dissipating power, to measure the currents and to discharge capacitors after power is removed. They are used in precision circuits to establish currents, to provide the accurate voltage ratios, and to set precise achievement values. In logic circuits, they act as bus and line terminators, and as pull-up and pull-down resistors. In high voltage circuits, they are used to measure voltages and to equalize leakage currents among diodes or capacitors connected in series. In radio frequency RF circuits, they set the bandwidth of resonant circuits, and they are even used as coil forms for inductors. Resistors are available with resistance from 0.0002 ohm through 10 to the power 12 ohm. Standard power ratings from 1 divided by 8 watt to 250 watts, and accuracies from 0.005% to 20%. Resistors can be made from metal films, metal oxide films, or carbon films, from carbon composition or ceramic composition moldings, from metal foil, metal wire wound on a foam, or from semiconductor elements similar to the field effect transistors, FETs. The most commonly used resistor types is formed from a carbon, metal, or oxide film and comes in two widely used packages: the cylindrical axial lead type, typified by the generic RN55D 1% 1/4 watt metal film resistor, and the much smaller surface mount chip resistor. These common types come in 5% and 2% and 1% tolerances. In the standard set of values ranging from 1 ohm to 10 megaohms, and the 1% types have 96 values per decade, where the 2% and 5% types have 48 and 24 values per decade. See Appendix C, Figure 1, Figure 1.2. Illustrates most of the common resistor packages. Resistors are so easy to use and well behaved that they are often taken for granted. They are not perfect though, and you should be aware of some of their limitations, so that you won't be surprised someday. The principal defects are the variations in the resistance of temperature, voltage, time, and humidity. Other defects relate to inductance, which may be serious at high frequencies. The development of thermal hotspots and power applications of electrical noise generation and low noise amplifiers. We treat these in Advanced Chapter 1X. Voltage to a current and vice versa. This may sound awfully trite, but you will soon see what we mean. B. Resistors in series and parallel. From the definition of R, some simple results follow. The resistance of two resistors in series, figure 1.4, is R is 1R1 plus R2. But by putting the R equations, we're going to see we're going to lose text. We're going to stop this because these are all equations we cannot read plainly. I want to read plainly. So this is Swift. We're going to close that down too. Here we are, elementos, algoritmo de buscada. Para otros, usos y términos de búsqueda. Un algoritmo de búsqueda es un conjunto de instrucciones que están diseñadas para localizar elementos considerados propiedades dentro de una estructura de datos. Por ejemplo, ubicar el registro correspondiente a cierta persona en una base de datos o el mejor movimiento a una partida de ajedrez. La variante más simple del problema es la búsqueda de un número a un vector.